Right now, buried under prairie fields, riding silently beneath the ocean on a submarine, or sitting on a mobile launcher hidden somewhere in a forest, there are machines built to do something almost absurd: leave the ground, climb out of the atmosphere entirely, coast through the vacuum of space, and come back down thousands of kilometers away, landing within meters of a single predetermined point. Total flight time, pad to target, often less than 30 minutes. This is how that flight actually works. Not the politics, not the payloads, just the physics and the engineering. Second by second. Let's break it down. Every launch starts in a state of readiness most people never see. Depending on the design, the missile is either fueled with storable liquid propellants kept ready for years, or, more common in modern designs, built around solid rocket motors, which are essentially preloaded, precast blocks of propellant sealed inside the airframe, ready to fire the instant they're commanded. No fueling process, no countdown fog venting off cryogenic tanks, just a sealed system waiting for a signal. When that signal comes, there's no astronaut countdown, no T-10. The launch sequence is handed entirely to onboard and ground computers because the timelines involved are far too fast for human reaction. Igniters fire, chamber pressure builds in milliseconds, and if every sensor agrees the motor is producing healthy, symmetrical thrust, the missile leaves its silo, tube, or rail in well under a second of visible motion. Here's the part that actually does the hard work for the entire rest of the flight: guidance. Long before liftoff, an inertial navigation system inside the missile has already been aligned. It knows precisely where it's starting from. Inside that system are gyroscopes, which sense rotation, and accelerometers, which sense every tiny change in velocity. An onboard computer integrates that data continuously, calculating position and speed without ever needing to look outside the vehicle. This idea isn't new. It traces back to German V2 engineering in the 1940s. And was refined through the early space programs of the 1950s and 60s. Modern systems add star trackers or satellite-based corrections to cancel out drift, but the core principle hasn't changed. The missile always knows where it is, because it's been counting every push and every turn since the moment it left the ground. The first phase of flight is called boost phase, and it looks a lot like any rocket launch, because physically it is one. The vehicle climbs vertically for the first few seconds, then follows a programmed pitch maneuver, tilting off vertical to start converting straight-up speed into the sideways, downrange speed the trajectory actually needs. Small nozzle deflections, gimbaling, fractions of a degree at a time, constantly correct the vehicle's attitude, fighting wind shear and keeping the thrust vector exactly where the guidance computer wants it. About a minute in, the missile punches through max Q, the point of maximum aerodynamic pressure, where speed and air density combine to put the greatest structural load on the airframe anywhere in the flight. Engineers design the vehicle's skin and control surfaces specifically to survive this narrow window, because a few seconds later, the air is already thin enough that the stress drops off fast. If the design uses multiple stages, and most do, for exactly the same reason as any orbital rocket, the first motor burns out, explosive bolts fire, and the spent stage falls away. A second motor ignites behind it, now pushing a lighter vehicle that no longer has to drag empty, useless casing along for the ride. Boost phase, start to finish, typically lasts only 3 to 5 minutes. By the time it ends, the missile has already been accelerated to several kilometers per second, and then silence. The motor shuts down, and the vehicle enters midcourse phase, a long, unpowered coast through the vacuum above the atmosphere. This is the part of the flight that looks the least dramatic and lasts the longest, sometimes 20 minutes or more, depending on how far the target is. With no engine running, the missile is now following a pure ballistic arc, shaped entirely by gravity and the velocity it was given during boost. Think of it the same way you'd think of a thrown ball, just scaled up to speeds of kilometers per second and an arc that peaks hundreds of kilometers above the Earth. During this coast, the guidance system isn't idle. It keeps refining its position estimate, occasionally checking itself against the stars or satellite signals, quietly correcting for any drift that built up during the noisy, vibration-heavy boost phase. At the top of that arc, apogee, the vehicle is moving at its slowest relative to the ground, and from here on, gravity is the only thing accelerating it. It's now falling, in the truest sense, back toward the atmosphere, picking up speed the entire way down. Reentry is where the flight becomes violent again. The vehicle slams back into the atmosphere at several kilometers per second, many times the speed of sound, and the air in front of it has no time to get out of the way. Instead, it compresses violently, heating to thousands of degrees and forming a glowing sheath of plasma around the vehicle, the same basic physics that lights up a returning space capsule like Apollo or Dragon. The deceleration forces here are enormous, and this is arguably the single hardest engineering problem in the entire flight. The re-entry vehicle has to survive heat that would vaporize most materials, using an ablative heat shield designed to burn away in a controlled manner, carrying that heat away from the structure it protects rather than letting it soak through. Through all of this violence, the re-entry vehicle isn't just falling passively. Small aerodynamic surfaces or thrusters make final trajectory refinements, correcting for any last errors accumulated over the entire flight, so that after coasting through space and burning through re-entry, the vehicle still arrives essentially where the guidance system calculated it would, minutes and thousands of kilometers earlier. That's the real engineering achievement here, not any single phase, but the fact that errors of a few meters per second during a 3-minute boost phase, if left uncorrected, could mean missing the target by kilometers after a half-hour flight. Precision at that scale is the entire point of the guidance system. So to recap, boost phase gets the vehicle out of the atmosphere and onto the right trajectory, using a guidance system that's been tracking its own motion since before liftoff. Midcourse is a long, silent ballistic coast through space, arcing under gravity alone, and re-entry brings it back through the atmosphere at enormous speed, surviving heat and deceleration that would destroy an unprotected structure, while still making the fine corrections needed to close out the flight precisely. Every ballistic flight, whatever its size or range, is really this same 3-act structure: boost, coast, re-entry, repeated with different scales of trajectory and different guidance hardware doing the correcting. If this breakdown helped make sense of how ballistic flight actually works, subscribe for more deep dives into aerospace engineering, and let me know in the comments which phase, guidance, midcourse, or re-entry you want covered in more depth next.